Okay, today's video is Physics Edexcel AS level paper 1, which is called Core Physics 1, and it's from the summer of 2022. Okay, so I did this with my students as a practice for their AS exam coming up soon, next week. So I want to make sure I upload this for anyone who's revising. Okay, so if you find my videos useful, please share them with your classmates and show your appreciation by liking each video you watch, because that's how it gets seen by a wider audience. So the first question, it says, which of the following graphs shows how the current through a thermistor varies with the potential difference? So if you increase the potential difference across a thermistor, remember voltage is joules per coulomb, you're basically energizing the thermistor, and when it gets hotter, the resistance of a thermistor decreases. So the resistance will decrease with voltage, okay, because it's a negative temperature coefficient thermistor, the ones that you need to know about for your exam. So if the voltage goes up, the temperature goes up, the resistance goes down, and if the resistance goes down, since I is on the y-axis, the gradient should get steeper if the resistance goes down, okay? Because the gradient is the conductance, if you like, rather than the resistance. So the only one which has a decreasing resistance with voltage is B. Now, D looks like it's going in the same direction, yeah, but it's the shape of a diode. So diode has a threshold voltage, which there is no conduction before you reach the threshold voltage, so don't get confused. It is similar in that the steepness is increasing with voltage, but it's not a thermistor. A thermistor goes smoothly up. The first one is constant resistance, so that will be an ohmic conductor. That'll be something like a fixed resistance. And this one is a filament lamp, okay, where the resistance increases with temperature, okay? So the answer is B. You need to know these shapes, and they will give it to you in different ways, so you need to make sure you've tried as many questions as possible. And it now says, which is the following SI base unit? So base unit means kilograms, meters, and seconds. So it has to be one of these two. You've got to work out which one is incorrect or which one is correct. So resistance is voltage over current, and voltage is joules per coulomb, yeah, and current amps. Amps is a base unit, so you can't change that. So it's joules, that's meant to say joules per coulomb, amps to the -1. And a coulomb is derived from an amp. So coulomb is amp times seconds, and a joule is a force times the distance, so it's a newton times a meter. A newton is a force, which is a mass times acceleration, so that's a newton multiplied by the mass, and you get kilograms, meters squared, seconds to the -2. So that's the joule. This is the coulomb to the -1. Okay, so that's coulomb to the -1. And there's amps to the -1 that we had initially. You didn't simplify this, and when you simplify it, you will find that you have 1 kilogram to the power of 1, meters to the power of 2, seconds to the power of -3, and amps to the power of -2. So there it is. Knowing your units really helps you work out equations. So it's something that you need to become strong doing. Any unit you find, you need to be able to put it in base units. Now the diagram here shows the path of a pollen particle on the surface of water as it is hit by water molecules. We call this Brownian motion. Yes, often studied in lower school, Key Stage 3. The scale is given to you as 1 centimetre to 0.5 millimetres. So, which of the following is the magnitude of displacement? So remember, displacement is a vector quantity. So it's how much has it moved from start to finish. So it's basically just a straight line drawn from straight to finish. Yeah, from start to finish. And it's a single arrow, which is displacement. So that's what a vector quantity means. You can replace it with a single arrow. You just measure the length. It's 8 centimetres. So 8 centimetres, 1 centimetre is half a millimetre. So the answer will be 4 millimetres, that should say. Okay? I got the unit wrong. So that's a mistake. That bit should be a millimetre. Anyway, the answer is 4. There's only one answer for, and that is D. Apologise for the mistake. A conductor has a resistance R. A constant potential difference is applied across the conductor. Yes. And then the drift velocity of the charge carriers in the conductor is V. So this is testing you on I equals NAVE. Yeah, in the Navy, how I remember it. Which of the following is the relationship between resistance and drift velocity? Well, we know they've given us the resistance. And of course you know that I is V over R. So you can replace I here with V over R. Yes. So, in other words, I is proportional to 1 over R, which is proportional to V. So V and R are inversely proportional. Okay? There is no square root involved. So the answer is C. Question 5, it has a variable resistor connected in the circuit as shown. The cell has internal resistance, so sometimes they're ignoring internal resistance, so it's about internal resistance. Okay, the resistance of the variable resistor is increased. The resistance is increased. If you increase the resistance, the current in the circuit will go down. Obviously, which row of the table is correct? Okay, well, if the current goes down, we're looking for a decrease, so it's got to be C or D. And if you have a decreased current, you're going to lose less voltage in the internal resistance. So if you lose less voltage, the voltage available in the circuit will increase. So it has to be C. Yeah, that's the only one that's going to be correct in both columns. Okay, so the answer is C. 5 questions done. 2 identical lorries, P and Q, carry different loads inside them so that the total mass of P is greater than the total mass of Q. So I've just put it like that. P and Q start from rest along the same road, so that's controlled variables. The force from the engine on each is the same, so these are all constant. F is constant, so nothing else is changing. Which graph shows how the velocity varies with time for the 2 lorries? Well, the one with a smaller mass, yeah, Q must have a greater acceleration. So the acceleration must be greater because everything else is the same, the force is constant. So you're looking for the steeper line initially for Q, and the only one that has a steeper line initially for Q is B. Yeah, you can see A, they start off with the same gradient. Yeah, in this one C is greater, so that's incorrect. And over here they're the same, so the only one which has a steeper line is B. Okay. There's the multiple choice answers from the mark scheme for the first 6 questions, in case you want to see how they present it. I have noticed that the Edexcel linear do not give much explanation in their mark schemes, especially the multiple choice, compared to the modular international A-level, okay? But they're not as bad as AQA, the one paper I've added. So if you know anyone who's doing AQA, I've added one AQA paper because no one else has seemingly done it. So I think it's one from last summer. A cable is used in question 7 to pull a mass of 2.5 kilograms vertically upwards, okay, with an acceleration A of 4.3 meters per second squared. Okay, which of the following gives the expression for the tension in the cable in newtons? So obviously downwards we have weight, therefore the tension up must be greater than the weight. So I've drawn the tension longer, so the resultant force will be tension minus weight, will give rise to the acceleration upwards. Yeah, so if we want to know the tension, put W on the other side, it's going to be MA plus MG. Yeah, so we're looking for MA, there's MA, there's MG, and it's the only one where they're added, so the answer is C. Question 8, a power station provides electrical power at a rate of 3,500 megawatts. 3,500 megawatts is 3,500 times 10 to the 6, or 3.5 times 10 to the 9. Okay. Which of the following gives the estimate of energy provided to consumers over a period of a year? They told you a year is how many seconds, so they want you to just use the equation power times time, multiply the power by the number of seconds, and it's going to be about 10 to the 17, so the only answer is D. So you don't actually have to do the full answer. You can see that it's going to be about 10 to the 17. Okay? So it's really just making sure you don't make mistakes with your prefixes. And that's the end of the multiple choice section. Well done if you got all 8 right. Question 9, it says a circuit was constructed as shown. So you got 30 ohms in series and 2 of the resistors in parallel. So you've got to work out the combination of those two, presumably. Work out the combination of those two. You'll get 17 ohms for the parallel section. And then for the total resistance, all you've got to do is that RT will be equal to 20 plus 17 ohms in the middle plus 10 ohms. So the total resistance will be as if you got a 20, 17 and a 10. So that's 47 ohms. 2 significant figures is all you can give. And that's a nice 3 marks. Okay. There's the answer. Question 10. A sprinter crossed the finish line of a race and then decelerated to rest. Yeah. The graph shows how the velocity of the sprinter varied with time once he had crossed the finish line. So in other words, he crossed the finish line at time 0. So this is the finish line. Yeah. So you can see he's decelerating. Yeah. Initially he decelerates gradually. Yeah. The deceleration is the greatest around here. Okay. But they want you to work out the distance traveled while he's decelerating. Now, one of my students was quite clever because they want you to work out the area under the graph. So you could work out how many 0.4 meter squares there are. So each of these squares is 0.4 meters. So you can count how many of them there are. But one of my students actually just drew a line from here to here. And you can see, well done, Swarali, yes, that this bit is the same shape, more or less, as that bit. And if it is, it looks pretty much the same, you can just do area under the triangle and you will be able to save some time. So area of the triangle is obviously half base times height. So it'll be, the area in the graph will be half times 1.2 seconds times the maximum velocity times 10. Yeah, so that's going to be 12, 6 meters. And I think that is the answer. So that will save my student who did that a bit of time compared to counting all those squares. She is an advanced mathematician. Okay, so obviously maths gives you an advantage in speed of problem solving in physics. So I always recommend that you've done at least AS level maths if you're continuing with physics. Okay, and yes, you can see they're accepting an answer between 6 and 6.2 meters depending on your method. Okay, that's how you get the marks. Question 11, it says the graph shows the resistance of an LDR and how it varies with light intensity measured in lux. Okay, so they got the lux light intensity units here, and they then use the LDR in a potential divider circuit where the 9 volts is divided between the resistance of the LDR and the resistance of a manually variable resistor. You see how you can draw these circuits with 9 volts at the top and 0 volts at the bottom, and that's how I recommend you to think of potential in the circuit. So you've got 9 volts there. If they were equal resistances, then in the middle would be 4.5. So this will be in the middle of the 9 volts to 0. So if they were equal resistance, it will be split 50-50. But if one is bigger than the other, then it won't be split 50-50. And presumably they'll want you to work out what the output voltmeter reading will be, yeah, depending on the conditions that they're looking at using the graph. And it looks like they're going to ask around the 12 kilo ohm position, yeah. All right, let's have a look and see what the question is asking. So that's the scenario. Now we're going to read it. The student increased the resistance of the variable resistor. Whilst the light intensity was constant, the voltmeter recorded the potential difference across the variable resistor, yeah, as shown in the diagram. Explain what happened to the reading on the voltmeter. Okay, so the reading on the voltmeter will increase, yeah. Why does it increase? The voltmeter reading will increase, okay, because the light intensity doesn't change, so the resistance of the LDR is constant, yeah. Resistance of the LDR is unchanged, but because the total resistance is increased, yeah, the current decreases, yeah, which is what happened to the read to explain what happened. So the resistance decreases overall, therefore the current through the two resistors will decrease, and since the voltage, the proportion of the voltage between the LDR and the fixed resistor or the variable resistor is now different, the LDR gets a smaller share, yeah, and the fixed resistor gets a larger share, so it gets a greater share of the EMF, which was 9 volts. Okay, so it gets a greater share of 9 volts because the student increased the resistance of the variable resistor. So the resistor with the higher resistance will get more voltage. So I was trying to do it in a different way, yeah, but I think the other way is better, okay? It's the same. If you read the notes, I've just put a green X through, they'll probably make sense to you as well, okay? The next question says the variable resistor was then set at a resistance of 4.5 kilo ohms. So we know that the resistance of the variable resistor, I put RR there. Determine the light intensity when the potential difference on the voltmeter was 2.5 volts. So if we know that the 4.5 kilo ohms, yes, produces a voltmeter reading of 2.5 volts, we can work out the ratio. So that we know the voltage of the variable resistor is 2.5. That means we know the voltage of the LDR from that, as being 6.5 volts. Okay, so once we know the two voltages and we know one of the resistances, the ratio of the resistances must be equal to the ratio of the voltages. So the only unknown is the resistance of the LDR. Put the numbers in and you'll get 11.7 kilo ohms. Yeah, but they want you to determine the light intensity. So you go to the graph, you use the graph and find the light intensity at 11.7 kilo ohms. Yeah, so go back to the graph. 11.7 kilo ohms is about there. So draw a line from 11.7 kilo ohms. Then go down. Work out the light intensity. It's around 180. And there you go. Bob's your uncle, as they say. So it could be slightly higher, but I think that's good enough for this question, and you'll get the marks. If you look at the mark scheme, you can see what you get marks for. Okay? Anywhere between 180 and 190, they will accept in that range. Okay, so I'll let you stop the video if you want to have a look at the notes for 11A and 11B. Okay. Next question is motion and relative velocity of a current and the boat having to direct its engines into the current so it finishes at the finishing point where it's trying to get to the other side. So a boat crosses a river to a point on the bank directly opposite the starting point. So you see the starting point and the finishing point are directly opposite. To be able to do that, because of the current of the water, it's got to head off in roughly this direction. Okay, so you're going to have these two arrows adding together, yeah, to finish at the starting point. So you basically got a vector addition question. So we know the current of the water, and they want you to use a scale drawing. So the boat is steered at an angle theta. Yeah, here you can see the boat is steered at an angle theta to the velocity of the water in order to travel forwards in a straight line towards the finishing point. So you've got to use vector addition. So hopefully Sophie got it right this time. The speed of the boat relative to the water is given as 4.3 meters per second. Yeah. So the boat is going 4.3 meters per second at an angle theta. There's the angle theta, I've drawn it. Now you know you want to finish exactly opposite. So you know that the resultant velocity should be getting you to the finishing line. So the 4.3 at the angle theta plus the 2.4 meters per second of the water current. Together, if you add those two arrows, which means you put the first arrow and then add the second arrow on top of the head of the first arrow. You can go either way, the parallelogram or rectangle in this case, because at right angle. And once you've drawn it to scale, has to be drawn to scale. One of my students had calculated it using mathematical ability, and you won't get the marks. If they've asked for a scale drawing, you need to do that. So I've put 1 meters per second to 2 centimeters, yeah? And they do want you to use as much, at least 50% in one direction of the available space provided. So you need to have a large diagram, yeah? Make it as large as you can without making it a difficult scale to read. So the resultant direction is known, as I said. So we know we want to get to the other side. So this is the finishing point. Yeah. And then once you've got the scale done properly, you can then use a protractor to measure that angle. And make sure, Devon, you give it to the correct horizontal, for example, or to the direction of the water flow, because remember the water flow is this way, so you can say the direction of the boat is 55 degrees to the current of the water. Okay. Our next question, it says the boat repeats the crossing at the same speed when the velocity of the water, the current of the water, is even greater. So obviously it would have to head off even more at an angle, yeah? So how will the time taken for the crossing change? So if the current is stronger, the time taken must increase, yeah? Because the theta, the 55 degrees, will now need to, the 55 degrees will decrease in that you'll be slanting more that way. So this angle theta will decrease, okay? So the new theta dash will be smaller than before. Before it was 55 degrees, is more like it was going like that. Now it's having to go that way. So the component of the boat's velocity across the river will decrease, yeah? Because the component would be, for the yellow angle, across the river will be a smaller one than if it was going that speed. You can see the component across the river is greater in the green angle than in the yellow angle. So original theta, and yellow one is the new theta, new situation. Hope that makes sense. Okay. Any questions, feel free to leave comments. By the way, from now on, if you become a member, you'll get priority in terms of your questions being answered. Yeah, obviously my own students can catch me whenever they want, but if you're watching these YouTube videos, I'm getting a lot of comments and questions, and we now got 1,200 or more subscribers, so there's now a membership available, and it will cost you to become a member, and then you will get priority treatment. So if you're a member, it will show up that you're a member, and it will allow you to get your questions answered as a matter of priority. Everyone else, you have to wait. Also, when you're asking a question, make sure you quote the minute in the video that you want me to look at, because obviously the quicker I can find it, the quicker I can respond. Okay. So sometimes people just say, why was it 70% or why was it 70? And they don't actually say which question they're looking at. I can't read your minds. Okay, so you need to bring clarity to it. Okay, I try to answer all questions eventually. All right, so, but as the number of subscribers increases, it will be difficult. So you do need to, if you want help, you need to make sure you become a member. It's not very expensive, but it's just a way of making sure you get priority. Here we have something called a trebuchet, which is a whole counterweight with the sling and the rock. So it's a medieval catapult designed to project a rock over large distances. So it's kind of a projectile. The rock becomes a projectile. And a simplified diagram is shown. Yes. So here's the way that you release the mechanism. Yeah. Presumably when you release it, the counterweight drops, and therefore this is flung upwards. Yeah. Okay, a rock is held in a sling, as shown. Yeah. So there it is, the rock in the sling. When the peg is removed, the counterweight falls, as I said, and the rock is projected through the air. Okay? The student assumes that all the gravitational potential energy is transferred from the counterweight. So this loses gravitational potential energy, and obviously the rock gains gravitational potential energy, but it also has it transferred to kinetic energy. But the student is wrong, because the student is not correct, because obviously the rock also gains gravitational potential energy. So but eventually it will become kinetic energy. So it's not that simple, but you do realize that there's not just the rock that gains energy. The beam also moves up, yeah? And the beam has mass, so there will be some kinetic energy for the beam. And you also will have some friction, so you're going to do some work done against the friction. So whenever there is any moving parts, there will be some friction. And obviously the other side also of the beam, it gains potential energy because it ends up being higher than it was before. So all of these are 3 points you can make to explain why the student is incorrect in assuming that it all goes to the transfer of to the kinetic energy of the rock. Okay, it doesn't all go to the kinetic energy of the rock. Here then, once you get the projectile motion set up, you then need to answer a projectiles type question. Rock was projected with a velocity of 41.5 meters per second. That's the initial velocity. Yeah, so I've drawn it as this green arrow. Okay, at an angle of 30 degrees to the horizontal. The diagram shows the flight of the rock after it has left the trebuchet. Yeah, the rock rises to a maximum height. So the maximum height obviously is there. Now what you've got to realize is the time to go up is equal to the time for it to come down, because gravity is the same acceleration and deceleration. So decelerates going up and then accelerates the same rate coming down. So it falls back to the same height. Yeah, so the same height will be here. When the vertical component of the velocity reaches 0 at the maximum height. So over here, the final velocity, here, the final velocity will be 0. Yeah? At the maximum height. Yeah. Okay. So once you know all of this data, in terms of, you always look at the vertical motion first. So when you're looking at the vertical motion, yeah, going up, we know that the vertical velocity will be u times sine 30, because it's going away from the 30 degrees. So you want to know how much is it going that way. So it's the component upwards. So it'll be the arrow projected upwards. Yeah, so that will be the u vertical. Yeah, it'll be the projection of u in the vertical direction, which is sine 30 or cos 60. That gives you the speed upwards initially. Final velocity upwards at the maximum height is 0. We know the acceleration is negative g, minus 9.81. You can work out the time it takes to go up. It's 2.12 seconds. So the time for it to go up is equal to the time for it to go down. So you know the time of flight, and they want you to calculate the horizontal distance traveled. So once you know the total time is 4.24 seconds, and there is no air resistance, we are assuming there is negligible air resistance, which you have to do in these equations. So that means that horizontally, the range will be the horizontal component of u, which is u cos 30, yeah, which is 41.5 cos 30, where times 4.24 the flight time. You put the time in there. I should put it into this equation. Once you do that, you'll see that it's 152 meters to 3 significant figures. So the horizontal distance, in other words, is the range of the medieval projectile machine. Okay? Then it says the mass of the counterweight is reduced. The trebuchet was then used to project the rock. Again, explain why. The horizontal distance decreases. Okay? Where you got less gravitational potential energy because the mass of the counterweight is less, so therefore you get less kinetic energy transfer to the rock. Therefore the vertical component of the launch velocity is also decreased. If the launch velocity is decreased, the time of flight is reduced. If the time of flight is reduced, the horizontal component of velocity will also decrease, and the time will decrease as a double whammy, so the range will decrease. Okay, so as long as you get all those points, you'll definitely get the 5 marks. Okay, and here's the mark scheme. Okay. All right, so here we got question 14, a student's traveling forwards at a constant speed on a skateboard. The student then jumps, as they do, these skateboarders, they jump off their skateboard. It's the Newton's third law effect. So if he jumps off his skateboard, yeah, you've got to explain how Newton's laws of motion apply to the student and the skateboard. So that's why the interaction between the student and the skateboard is Newton's third law. As he jumps forward off the moving skateboard, so at first they said the student jumps forward. So if the student jumps forward, yeah, by jumping off the skateboard will get a force backwards. So if one force, this is Newton's third law effect, if one object gets a force forwards, then the other object will get a force backwards, and they're going to be the same size force on the two different masses, but the forces will be equal and opposite. So if he jumps forwards, yeah, there's an equal opposite reaction on the skateboard. Okay, that's the skateboard. The force on the skateboard is the one applied by the student's jump, pushing the skateboard back, because that's due to Newton's third law. Okay, so by Newton's third law, the force from the skateboard on the student and the force from the student on the skateboard must be equal and opposite. Okay, the two forces are the same type, must be of equal size, but in opposite direction. And obviously they're simultaneous, they last for the same amount of time, because it's to do with the contact. The student accelerates forwards, now it's Newton's second law. You're now looking at only one object, whereas here you're looking at two objects with opposite direction forces. Now you're just looking at one object. When you look at one object, we're talking about Newton 1 and Newton 2. But if there is a accelerating force, then we're not talking about Newton 1, we're talking about Newton 2. So the student accelerates forwards as a result of the force on him, yes, by the skateboard. So that's Newton 2. Forwards must equal acceleration forwards. The skateboard, on the other hand, has the same equal and opposite force, so it accelerates backwards. Yeah, so it decelerates, if you like, because it was moving forwards initially. The force is backwards, so the acceleration is against the motion, again by Newton's second law. Okay, again, you're looking at one object at a time. Yeah, whereas Newton's third law, you're looking at both objects at the same time. So, as the mass of the board is less than the mass of the student, the magnitude of the acceleration will be greater on the skateboard than on the skateboarder, okay, the student. Okay, and that's, I think, answered the question. Now, how they give the 6 marks, I'll let you look at the content indication that they're looking for, and then they'll look forward to the structure of your answer. Yeah, if you read this, your ability to communicate clearly. So I always tell my students who want to do physics A level, I say, physics equals English plus maths divided by 2. So you need to be good at maths and you need to be good at English. And in fact, most students find the qualitative answers much more difficult than the mathematical ones. Okay? As I said, if a maths teacher can do it, it can't be that difficult. Just teasing my maths colleagues. Okay? So an electric motor, question 15, is used to pull a truck up a slope at constant speed. Whenever they say constant speed, they're talking about balance forces. So it's going to be Newton 1. The electric motor circuit includes a battery with no internal resistance, an ammeter, and a very high resistance digital voltmeter. Remember, good voltmeters have high resistance, so they don't take much current from the main part of the circuit where you want the current to flow. If they did take current, they would actually affect the current that they're meant to be measuring. It says, part A, the truck moves through a vertical height of 0.2 meters in 15 seconds. So it's the rate of gain of height. Yeah, you could say it's joules per second. So you could work out the joules per second. So in A level, you've got to get used to the fact that you've got to work out the rate of change of things. Yeah, including, for example, the rate of flow of water jet, for example, will be kilograms per second. Okay, The current in the motor is given in milliamps as 88.1 milliamps. So you've got to change that to amps, 10 to the minus 3, and the potential difference across the motor is exactly 12 volts. Yeah, the mass of the truck is 550 grams. You need to change that to kilograms. Okay, so don't forget, you've got to change this to milliamps, to amps, and grams to kilograms. We don't use grams as our SI unit. The SI unit is kilograms. So calculate the efficiency of the motor. Well, the power in the motor is voltage times current. Change that to 10 to the minus 3. So 10 to the minus 3 is the important bit. And you get the power input from the motor as 0.0972 to 3 significant figures. You don't need to put more than 3 significant figures, even as an interim calculation. The power output is the rate of increase of the potential energy. So it's 0.55 mass times gravity times the rate of increase of height, 0.2 meters in 15 seconds. So you can just do mgh over time, and you'll see that to 2 significant figures gives you a value of 0.0702. To work out the efficiency, you put your output divided by your input, and you get 74% or 0.74 efficiency. Okay? Now, efficiency can be as a fraction or a decimal. Doesn't have to be in percentage terms. But if they ask for percentage, then you get, you will be expected to put in percentage. So be careful when you're reading questions. A lot of marks are lost by students when they think they've read the question carefully. Okay, that's why you should underline things when you're reading it. Be active, don't be passive when you're reading. The digital voltmeter is replaced with an analog voltmeter with a much lower resistance. Yeah? So voltmeter will now draw current. Before, the current was negligible, it couldn't be measured by the ammeter. So the current in the circuit and therefore the battery increases. Yeah? Some power, energy, is therefore also going to be used and dissipated in the voltmeter itself, because if it's got current and it has a resistance, it's going to use up some power. So power output of the battery will need to increase because it's basically got another component in parallel which is having to feed with energy. Yeah? For the same work done. Yeah? The output of the battery will increase, therefore the efficiency will decrease because some of it is being lost in the voltmeter. Yeah? Remember, there was no internal resistance in this question, otherwise it would have been something else to speak about. There's 4 marks, I've got 4 bullet points, and here's the mark scheme. I'll let you stop the video, pause, have a look at your own answer. And if you're one of my students, don't forget, you can always come and ask questions if you find me in a one-to-one moment. Okay? All right. There was a student on YouTube that was asking for whether I do private tuition. I do private tuition, but only on rare occasions and usually face-to-face. I don't really like doing things online. But if you really want a recommendation, I do know someone who in the UK who does it online, and he's very good. Okay, the string pulling the truck was cut. Yeah, so if that happened, where was the truck? It was going up the slope. The truck A then traveled down the slope again. Yeah, onto a horizontal surface and collided with the second truck B, which was initially stationary. So it looks like they're wanting you to do a momentum question. So you got the truck A going and colliding with truck B, and truck B was initially stationary. Okay, the velocity of truck A just before the collision was given, yeah, as 5.4 meters per second, 5.4 meters per second. Okay, so initially the truck A had 5.4 meters per second, and obviously truck B was 0 meters per second. Okay. Determine the velocity of truck B after the collision. Yeah. So, and after the collision, truck A went down to 2.1 meters per second. So the total momentum before was all due to A. So you can almost, the B was 0. I put it in there for the sake of completion. So you multiply the mass by the velocity. Yeah, the mass is given here. You've got to change to kilograms. Yeah. And then afterwards it went down to 2.1. The mass hasn't changed. And therefore we know the mass of truck B is 350.35. The unknown, the only unknown is VB. So you've got to find VB, change the subject of the equation. You'll see that this will give you the correct answer. Okay? Answer is 5.2 or 5.19 to 3 significant figures. And that's another 11 marks done. Okay? There's the answer. 15C. I'm whizzing through this in one video because I just don't have enough time to stop and do it again. Each time I stop, I have to upload it, I have to wait for YouTube to do it. So obviously I'll get more viewers if I did it in 2 videos, but I've got other exams to prepare as well. A lot of students are preparing for exams right now. Question 16. A student investigated how the supporting forces on a bridge vary as the load or the traffic moves across the bridge. So they're representing it with a load here. Yeah. The student made a simple model, yeah, as shown using a meter ruler. Meter rule is the way we pronounce it for those of you who think it should be spelt meter ruler. Okay, the meter rule rested on 2 supports at P and Q. So obviously the weight of the load and the ruler are balanced by FQ and FP upwards. So the upward forces must balance the downward forces. The upward force on the ruler was FP and FQ, as I've just mentioned. The load was placed on the meter ruler at distance x from support P. Forces P, FP, and FQ were measured for different values of x, so they're doing an investigation. Explain how FP and FQ changed when x was increased. Well, if x increases, yeah, then if we take moments about P, so just assume you're going to take moments about P. So we're going to take all the moments about P. So if the x increases, when x increases, yeah, the clockwise moment will increase. So if x increases, the clockwise moment due to the load will increase because it's got further away from FP. So for equally, the clockwise moments must equal the anti-clockwise moments about FP. Okay, so I should have written it in a better way. When x increases, the clockwise moment due to the load increases. So then FQ will need to increase to produce an anti-clockwise moment equal to the new clockwise moment. So FQ will increase. Okay, so as x increases, I've said the clockwise moment of the load about P increases. So I should put this first. Okay, as FQ must increase as a result to balance the moments anti-clockwise about P. Okay, to balance the moments. So in other words, clockwise moments must equal anti-clockwise moments. I could have chosen my words a little bit more clearly. If FQ increases, yeah, then FP will decrease. Why? Because the sum of the downward forces hasn't changed. So the sum of the vertical downward forces has not changed, and we have a balanced force situation. So the upward forces FP and FQ together must still equal the same amount. Okay? Because FP plus FQ, we know is balanced forces, must equal the weight of the load, which is constant, and the weight of the bridge, which is constant. And that allows you to get to the end of section A, 59 marks. Okay? So now, for Sophie and Evan, section B is their favourite part. Okay? So question 16, there's the answer for the mark scheme. Okay? Alternative, you could do moments about Q. So just keep your moments about one side. It's easier to do about P because the distances were given to the load from P. Okay, so section B now seems to be more an application of physics. All questions can be from any part of the syllabus. The diagram shows a wooden meter rule again, which is clamped horizontally to a bench. Yes. The other end of the ruler is loaded with a weight. So the weight is here, right at the end. I have a feeling I've done this question before in another paper. The length L of the meter ruler, or the meter rule between the clamp and W can be varied. So the length L is this length. In fact, that would be your independent variable in this investigation. The loaded end of the ruler is then displaced through a distance D. So this D depends on the length L. So you change L and the weight will have a bigger impact. They're keeping W constant. Okay, I've drawn my ruler upwards so I can measure things accurately. See the way I've drawn my ruler? Yeah, that's how I want you to draw it when you're doing your exam technique. A student investigated how D varied with L, so that's our aim. How does the independent variable affect the dependent variable? Okay, so I put a second meter rule here, and they're going to ask about that in a minute. Describe how the student should use set squares and a second meter rule to determine D. You may add to the diagram. So I've added to the diagram. I've shown that my meter rule is vertical by putting a set square on the floor. Don't let your ruler be floating in midair. You want the floor to be the starting point. Okay? Now, normal benches in labs are about 90 centimeters high. So a meter ruler will work and will reach the unloaded ruler position. So you put the set square to check for vertical, the vertical sense of the ruler. Yeah, you put a set square to measure the deviation from the original position, and you want to make sure you've got your starting point of your ruler again with another set square position there. So that's a very good way of showing that you know how set squares are used. So whether you're doing linear or modular, this skill is required. So set square 1 to ensure ruler is vertical, set square 2 and 3 to measure D accurately from the starting point or precisely, and to avoid parallax, which is a form of random error. You need to get to eye level, and the set square ensures that you're measuring at eye level to the correct position of the ruler to the nearest millimeter if possible, and that will get you 2 marks. Okay. 17b is looking at range of data. Yeah. So remember, uncertainty is half of the range of data if you've got multiple readings. Okay. So here they got multiple readings, 4 readings of whatever t is, and the average is given to you. And the range is from 6.24 to 6.29. So half the range will be half of 0.05 millimeters, and that is what you use to work out the percentage uncertainty. It's half the range divided by the mean value. Yeah? So you put the mean value in there, and you put half the range in there, and then half the range will be 0.05 divided by 2, divided by the mean, gives you an uncertainty of 0.40%. They're giving you an equation here, yeah, that you're going to use later on. So you need to make sure you've read that. Okay, so the student used the following equation relating deflection D downwards with the length of the rule. So D and L are both given in there. So D is on the left-hand side, L cubed is at the top, and then you've got a value of T cubed in there. So whenever there's a power, the percentage uncertainty comes in for a power of 3 times. So you've got to add the percentage uncertainty or multiply the percentage uncertainty by 3. Okay? And E is the Young's modulus of the wood. Yeah? B is the width of the ruler, and T is the thickness of the ruler. Okay? So they're giving you the value of the thickness of the ruler in this table. Okay? So once you've worked out the percentage uncertainty, they want you to then do a graph. So here's the student's results in a table. Yeah? They want you to plot D against T cubed, or L cubed, sorry. So D on the y-axis, and then they want you to use the additional column for your process data. Well, if you want D against L cubed, you've got to make sure you've worked out L cubed. Yeah? L cubed would then be in meters cubed. Yeah? And you want to have a consistent number of decimal places. Okay? They say 3 significant figures. I say use 3 decimal places. Okay, when you're taking measurements, you always have a consistent number of decimal places like here. Okay, so sometimes they talk about significant figures. Okay, so you see over here, they're all in millimeters, but you have the different number of significant figures. So I think decimal places are a better way of bringing in consistency. And I think the exam boards have not clarified that well enough. So there's a graph paper. I'm not doing the graph. If you want to do your graph, great. I haven't got time for that. So I'm using the examiner's graph. Luckily, he gave me his figures. So they're saying L cubed to 3 significant figures. I'm saying 3 decimal places. I'm right, they're wrong. Yes, because over here, it says accept 2 or 3 significants in table for the first 2 values. Yeah, so that's what they're talking about. So in other words, they're saying this is 2 significant figures. Well, I'm saying if you just talk about 3 decimal places, you'll get it right in the first place. Okay? Now, both axes must be labelled with the correct units for 1 mark. Yeah, so L cubed in meters cubed and D in millimeters. Yeah, you need to have good sensible scales, and the scales should always be multiples of 1, 2 or 5. And you've got to cover at least 50% of the graph paper. You can't do small graphs. So sensible scales going up and easy to plot scales. The plots, they will check. They're saying they're checking all the points. Now, often, I think what they'll do is they'll look at the 2 which are furthest away from the line of best fit, and they'll concentrate on those and see if you've plotted them to the correct square. And if you're more than half a square out, you could lose your plotting mark. Yes, so be careful with your accuracy, and then draw the line of best fit. And by the line of best fit, they mean that you have equal points scattered on each side of the line of best fit, because they won't always go exactly through all the points. All right, so that's how you get it. Now you see the way I've drawn my gradient on the graph. That's a good habit to get into, because you've shown you're working clearly, and the examiner will know that you're a serious and a good student. Okay, so I've put from 160 down to 0, and obviously this is 10 to the minus 3 because it's millimeters. And this is where you need to change the unit. You didn't need to do it for the plotting, but you do need to do it for the gradient, because they have to be in consistent units. Okay, now you can see it doesn't quite reach the origin. So on the delta x, you have to remove whatever the intercept is here, 0.01. Okay, I'm using the values given by the mark scheme. Okay, so once you've got that, they're giving you several types of wood, and you've got to work out which wood you think the rule is made of. So deduce the type of wood from which the rule was made. They've given you all the data you need for the equation that they gave you earlier. Yes. And they're giving you values in centimeters and millimeters. You've got to change it into meters. Okay. So they've given you D on the y-axis. So if D's on the y-axis, then the gradient will be the thing in front of L cubed, because L cubed was on the x-axis. So we know the gradient that we calculated must be equal to this term here in this green circle. So we know the gradient is 0.327 from the data I've shown on the examiner's graph. So you put 0.327 equal to this, or better still, change the subject of the equation first, because you want to calculate E. So you can compare the E to the values of E given in the table for 4 different types of wood. Put the numbers in. So the gradient goes down there, because you swap the E with the gradient. Yeah, can you see? They swap them round. So E goes to the left-hand side. Put the numbers in carefully. You'll get a value of 9.2 gigapascals, 10 to the 9, to 2 significant figures. It's closest to the Douglas fir value in the table. It's actually only a 5% difference, which is quite common to be 5% off when you're doing practicals, okay, because of the uncertainties in your measurements. Okay, so the closest is in the same range, Douglas fir. Okay, so you'd have to say that's what you think it most likely is. Okay, there's the gradient. Okay, you can see that they want you to use a large triangle. So if you're using a large triangle, show your values on the graph. It's a much better technique. Okay. Question 18, the last question. Wow, I've not one of these papers in one go before. At least not for a while. The student was given a block of something called conducting putty. Yeah, mass was given, so you've got to change to kilograms. Show that the volume of the block was about this. 8 times 10 to the minus 6 meters cubed. The density is given to you. So we know density is mass over volume from GCSE. You've got to work out the volume. We know the mass. We know the density. See, I made a mistake putting them upside down first. Put them the right way. You'll get 8.11 times 10 to the minus 6, which is approximately 8, because this is only to one significant figure. Okay? So one significant figure, you have shown that it is correct. Okay? The next part, it says the student formed the putty into a cylinder. Coins were then pushed into the ends, as shown. So you've got a coin here and a coin here. Can't quite see them on this photocopy. The coins each had a crocodile clip attached, and an ohm meter was then connected across here. So you've got an ohm meter attached there. That's meant to show that that's an ohm meter. Okay, there's my ohm meter attached to 2 crocodile clips. Determine the resistance of the putty. Well, they've given us the diameter as 12 millimeters, so don't forget, you've got to make that into meters, 10 to the minus 3. Once you've got a diameter, you can work out the area. Yeah. The cross-sectional area, which comes out to that. You probably get a mark for doing that correctly. And then you know you can use the resistance formula. Yeah. They've given us the resistivity. And length can be obtained from the volume and the area. We know that length will then be the volume divided by the area. We know the volume from before. We just worked out the area, so you put the area into this equation, and the volume from the previous part, you get the length of 0.0716 to 3 significant figures. So the volume was known from part A1. And you get a resistance of 2.54 if you do the maths correctly. 3 significant figures, but you can round it up to 2 because the data provided is only known to 2 significant figures. Okay, here the final part of the exam. The student then made a cylinder that had a larger resistance. Well, how do you get a larger resistance? Make it longer and thinner. Yeah? Explain how the student made a larger resistance. Make it longer and thinner. Thinner and longer will increase the R. Why? Because R is proportional to L, and R is inversely proportional to A, because we know the resistivity equation. I think that's quite a generous, easy end to the paper. So section B seems to be practical skills, application of physics, added to the 60 marks roughly from the more theoretical, gives you a total out of 80. I hope you enjoyed that video. Hope you found it useful. Hope you're going to support my channel. So if you're my students and you're watching my videos, I expect you to give me a like each time, and also sometimes write me a friendly comment, because I'm working hard in the evenings just to make your life easier. Okay, so thanks for watching. Catch you next video. Bye for now.